Welcome to this ELV Engineering Explainer. Today, we're taking core network switch design principles and translating them into what is, honestly, the ultimate unsung heart of every IP camera system. We're going to dive into exactly how to architect a setup that absolutely will not fail when you need it the most.
Think about this. An entire wing's security depends completely on rigorous switch engineering. If you're relying on just a single standalone switch, well, a simple hardware glitch can instantly black out 24 or more cameras. No way around it, we have to design networks with zero single points of failure.
So here's our blueprint for today. We're going to cover the 3 layers, switch sizing parameters, stackable versus chassis setups, essential protocols, IDF and hotel design, and we'll wrap it all up with 3 golden rules.
All right, let's jump right into Section 1, the threat and 3 layers. We need to structure the network hierarchy to mitigate catastrophic failure, especially in massive systems of up to 800 cameras.
Physically, this architecture builds out across 3 distinct stages on your site. First up is the access layer. These are your PoE-enabled switches, usually your 24 or 48-port models, tucked right into the floor IDF rooms so they're physically close to the cameras, minimizing cable runs. So the cameras hit the access layer, and then that access layer feeds into the aggregation layer in your main IDF. Now, aggregation uses higher port speeds and doesn't need PoE. Finally, aggregation pushes everything all the way up to the core layer. That core is the absolute top of your hierarchy, acting as a redundant pair in the main equipment room, connecting straight to your recording servers and storage.
Moving on to Section 2, 4 switch sizing parameters. It's time to calculate our required capacity using port count, PoE budget, uplink speed, and redundancy. Okay, so the golden rule for port counts is that you've got to plan for your current camera totals plus exactly 20% spare capacity, literally 20%. For example, if you have a 60-camera floor, you actually need a 72-port equivalent. Practically, that means you need 2 48-port switches stacked together, not just one maxed-out 64-port chassis. You always need breathing room.
Now, what's really fascinating here is the strict correlation between camera counts, megapixel resolution, and the absolute minimum uplink speeds you need to prevent nasty bottlenecks. Look at it this way. If you have up to 30 cameras running at 4 megapixels, a standard 1 gigabit uplink is totally fine. But the moment you push that to between 30 and 60 cameras, you've got to bump it up to a 2.5 gigabit multi-gig link, or bond 2 1 gig links together using LACP. Now, for 60-plus cameras, or any 8 megapixel deployment, there's no question you must jump to a 10 gigabit SFP plus uplink. Oh, and remember, your aggregation to core connection should absolutely be a 10 gig minimum, period.
That brings us to Section 3, stackable versus chassis design. Let's figure out how to choose the right form factor to actually achieve all this hardware redundancy.
For ELV CCTV setup specifically, stackable switches are hands down the superior choice for pretty much any project under 1,000 cameras. Stackables are just individual units connected by physical stack cables, which lets them act together as one single logical switch, complete with redundant power and uplinks. They're cheaper and honestly, way easier to expand. On the flip side, chassis-based switches are these massive, highly expensive modular boxes. Don't get me wrong, they're powerful, but they should really be reserved strictly for the enterprise correlator.
So when you're writing out your specifications, you absolutely must ensure that they include PoE++ on every single port. Over in the META region, for instance, specifying a really high-quality stackable, like the Aruba CX6300, is the undeniably correct engineering answer, like 95% of the time. It's just a rock-solid default.
All right, on to Section 4, essential CCTV network protocols. Because hardware alone won't run a stable video network, we need the software rules to route massive data flows efficiently.
The very first one is IGMP snooping. Listen, if you forget to enable IGMP snooping on switches that handle multicast video to multiple operators, your entire network is basically going to choke itself to death, literally. Without it, those multicast packets will just flood every single port on the switch like a broken pipe. But with it enabled, the switch gets smart. It intelligently forwards the video streams only to the specific ports that actually subscribe to that group.
Next up is LACP, or link aggregation. What this does is bundle multiple physical links together into one logical link. It's a real game changer because it provides the capacity for parallel flows summed across those links and, crucially, gives you automatic failover. LACP absolutely must be configured between your access, aggregation, and core layers so you can survive an uplink failure seamlessly without anybody noticing a drop.
But wait, we need to clear up a major engineering misconception right here. While LACP is fantastic at combining capacity from multiple parallel flows across the network, a single TCP flow will stubbornly only use one link at a time. It's true. So please do not expect LACP to double the speed of a single massive file transfer. That's just not how it works. It's there to handle the aggregate traffic of dozens of independent concurrent camera streams.
Finally, to prevent nasty network loops from crashing your entire system, you absolutely must deploy a spanning tree protocol. But hear me out, you must use Rapid Spanning Tree Protocol, RSTP or MSTP, and specifically avoid using the original older STP iteration. And the convergence times tell you exactly why you need to avoid the original version. When a link breaks, original STP takes a massive 30 to 50 seconds to converge. Think about that. You simply cannot afford an agonizing blackout of your security video for nearly a minute. RSTP, on the other hand, recovers and converges the entire network in a rapid 1 to 2 seconds. It's literally a no-brainer.
Okay, let's look at Section 5, IDF Planning and Hotel Design. This is where we take our blueprint to reality by planning an actual IDF cabinet and examining a real-world reference design.
Every single floor's IDF cabinet requires these very specific components, acting as that reliable physical bridge between your end devices and the wider network. You're going to need your 1 or 2 PoE++ switches, a patch panel matching your camera cables, a small fiber patch box for the uplinks, and, depending on the ambient temps, some optional cooling. But here's the kicker. Your UPS must be sized not just for the switch itself, but for the switch plus the maximum potential PoE load of every single attached camera. Let's apply this practically to a 5-floor, 200-camera hotel reference design. With an average of, say, 40 cameras per floor, each of those 5 floors gets a 48-port PoE plus access switch with dual 10-gig fiber uplinks. It's a really elegant progression. You're pushing that data down to the main IDF, which houses 2 stacked aggregation switches. From there, those switches push dual 40-gig uplinks straight into the redundant core backbone that connects to your servers. It's clean, redundant, and highly capable.
We made it to Section 6. 3 golden design rules. Consider this your essential checklist to lock in everything we've just covered. If you only take away 3 things from this explainer today, make absolutely sure they are these. Number 1, always calculate your PoE budget based on the full maximum power of all camera classes. Totally ignore average PoE calculations. Number 2, strictly mandate IGMP snooping on any switch handling multicast video. And number 3, ruthlessly eliminate single points of failure at the access layer by stacking your switches for any system larger than 24 cameras.
Because think about it, on a freezing morning when every single camera heater kicks on simultaneously in the cold, a PoE budget sized merely for average use is going to instantly overdraw and crash the entire network. That leaves your security team entirely blind. So the question is, will your design survive? Make sure you apply these standards. That wraps up network switch design. In our next explainer, we'll be diving into cabling for IP CCTV and the strict 90-meter rule. So subscribe and keep building.